And if you've made it this far and you're a real mathematician, then before I move on, please join me in reciting the statement of the Poincaré conjecture. Anthony makes videos. Let's do this shit, man. Realer than transcendental realism. Them niggas Newton and Einstein really had autism before the diagnosis was a thing. I'm just being honest, I ain't trying to diss them. Still a condition. Bitches think I'm weird, it's a blessing, I'm on my mission. Game like 9/11, call it terrorism. My sous chef is missing, I don't need him. I'm a chef in the kitchen, and I ain't kidding. I'm getting kissed with a twist of wisdom. Won't stop making videos till this book is done. I don't know. So, salut tout le monde. In today's video, I'm going to continue reading from Chapter 3 of Differential Geometry by Erwin Kreyszig. But first, I'd like to motivate why bother learning about differential geometry at all, right? So what sort of real-world applications for differential geometry are there? And also, in the description of my last video where I was reading about the basics of tensor calculus, I linked what I think was a really good video explaining visually and conceptually what a tensor is, and it was by this guy named Dan Fleisch. And it's a good video, but I think he said the most important thing of the whole video at the very end, and he should have tried to say it towards the beginning, which is that tensors are a data structure where the basis vectors and the components transform between reference frames so that the combination of basis vectors and components stays the same. So when we say that Einstein used differential geometry as the language for general relativity, which has something to do with non-inertial reference frames, and differential geometry has something to do with tensors and manifolds, how did we get there, right? So what is this all about? So I'm going to begin attempting to answer this by considering the so-called Copernican revolution. The word revolution in the term is critical because it points to a paradigmatic shift that is occurring with what Copernicus is introducing. It goes almost without saying that to the left on the screen now is Ptolemy, who lived from circa 100 to 170 Anno Domini. And Ptolemy is of course known for advancing in his work what would be the most authoritative mathematical model of the solar system from late antiquity through the Middle Ages. And this model of Ptolemy's happens to be geocentric. So this model is reputed to have been based upon astronomical observations spanning over 800 years. And as published in his book Almagest, or the Mathematical Treatise, Ptolemy accompanied his model with convenient tables that could be used to compute the future or past position of the planets with. So Ptolemy's geocentric model was clearly based upon a long duration of observation and was adequate for what people needed for over 1,000 years. So why is Copernicus's move to heliocentrism a revolutionary move? And why is it not regarded as merely changing minor premises in a more established model? After all, while Copernicus's model leads to obtaining a more accurate calculation for the length of a year, for example, Copernicus's model still maintains that the orbits of the planets are exactly circular, which of course is not the case. So I think the revolutionary aspect of Copernicus's heliocentrism is centered upon the metaphysical turn implied by Copernicus advancing a model centered about the sun, apropos Ptolemy's model centered about the Earth. So before, under geocentrism, the Earth is the center of the then known universe, and therefore is the moral center of the universe, and so too therefore are humans the moral center of the universe, and so too therefore the Catholic Church is the capital moral institution on earth, with the Pope at the top. Therefore, adopting Copernicus's model amounts to removing the Earth from the moral center of the universe, and that seriously undermines the Catholic Church, which was surely under its fair share of pressure with the overall Protestant Revolution going on roughly around this time as well. Nevertheless, Copernicus's model is an elegant reformulation, least of all for its simplicity, and that the motion of the astronomical heavens go on as they have and always will in some sense, but all that Copernicus is offering is a shift of perspective that leads to a more accurate understanding of the astronomical reality. Now, René Descartes would be born in the decades shortly after Copernicus's death, so this is before the Cartesian coordinate system has been properly introduced. Nevertheless, Ptolemy essentially had a reference frame for what we now call the solar system that oriented itself about the Earth at its center, and Copernicus's model shifted that implicit coordinate system of sorts to have the sun at the center instead. So with this being said, we can now take a step back and consider more generally what we take for granted as the concept of Newtonian gravity. One of the key mathematical takeaways of Newtonian mechanics is that it takes the motion of the heavenly bodies on the one hand and the equal rate of change of the rate of falling objects near the surface of the Earth on the other hand, and makes it so that both of these phenomena of macroscopic masses can be explained and accurately predicted with a single foundation, basically. In order to achieve this, however, we need two things: clocks and a coordinate system. And this can take you very far, except until you consider non-inertial frames of reference, such as being in a spinning room. Newton surmounts this by advancing absolute space, which addresses the coordinate system aspect of the two things you need to do this in practice. In fact, Newton says in Principia something to the effect that there exists a cosmic substratum which, in its own nature and without reference to anything external, remains always similar and immovable. Newton continues by saying that relative space, on the other hand, is some movable dimension or measure of the absolute space which our senses determine in its position to other bodies, and which is commonly taken for immovable space. Therefore, we can think of centripetal and centrifugal forces in Newton's framework as the result of the acceleration of our reference frame during rotation with respect to this absolute space. Interestingly enough, the debate between Leibniz and Newton and their followers over space would be critical to Immanuel Kant's formulation of Transcendental Idealism in his work, The Critique of Pure Reason. This debate is between space absolutism, which was Newton's take, versus space relationalism, which was Leibniz's take. Is space in and of itself perceptible or not? And if space is imperceptible, then how do we represent it? And can space be understood as a sensation or as an intuition? And what is the difference, if any, between empty space, the absence of space, and so-called extra-mundane space? And as an aside, extra-mundane space is, for example, what you might think of when asked, if you went to the very edge of the universe but tried to look further out or beyond that edge, what would you see? And some would say that you would then be looking into what would be called extra-mundane space. As I mentioned earlier, Newton, as part of his mechanics that he devised in Principia, adopted the metaphysical stance of absolute space in developing his system. Leibniz would not share this stance and instead would argue that space is ontologically dependent on objects and their relations. Leibniz, if he were around today, might say something along the lines that if you were implementing a supercomputer simulation of the universe, it would maybe go roughly as follows. You would have a data structure with entries for all the particles in the universe, and you would start at time t equals 0 at the Big Bang with all of these particles infinitely compressed into a single location. And then, one Planck length unit of time after initiating the Big Bang, the universe would be one Planck length in all space dimensions, and all of the laws of physics as we know them would be in effect thereafter. But tabling for now the details of the supercomputer, the laws of physics and how they're implemented, and the details of the Big Bang expansion narrative, etc., Leibniz would point to the entries of the data structure encoding all of the mass of the universe, and that for any two different time slices of the simulation of the universe, the relations between those entries of the mass data structure are the fundamental information representing the state of affairs of the universe, and space is just an emergent, almost almost illusory aspect of those relations. So thinkers like theologian George Berkeley, who I mentioned in a previous episode, had argued for immaterialism, namely that material substance cannot exist without being perceived, and that this perception is the result of empirical intuition. Call it transcendental realism. Kant would thus make the transcendental idealist move by clarifying Newton's absolute space in view of the scope of the debate with Leibniz's space relationalism, while also criticizing the transcendental realism of Berkeley. So essentially, Kant's take is that space is not a property of things independent of a priori intuition. The depth of Kant's full take on space per his critique of pure reason and the nuances of his transcendental idealism exceed the scope of this video, but for now we can refine this by considering briefly Kant's four antinomies of reason. Now, antinomies, to recall, are paradoxes that in this case Kant uses to demonstrate the limits of critical reasoning at apprehending the true nature of reality. A notable example of an antinomy would be the barber paradox, where a barber is the one who shaves all those and those only who do not shave themselves. So the question is then, does the barber shave himself? Now, Kant's four antinomies of reason as statements of such sorts of paradoxes are structured as pairs of a thesis and an antithesis. It goes that pure reason could be carried to its end and assert either the thesis or the antithesis, yet also by reason it is obvious that the thesis and antithesis contradict each other, thus suggesting a limit or irrelevance of critical reason in providing insight into the truly real transcendental ideal nature of reality. Furthermore, the four antinomies are categorized as the two mathematical antinomies, that is, one antinomy of space and time and another antinomy of atomism, and the two dynamical antinomies, that is, one antinomy of spontaneity and causal determinism and another antinomy of necessary being or not. The first mathematical antinomy is most applicable to understanding a refinement of part of Kant's overall philosophical view on space and time, which is related to how Newton conceived of the world to develop his mechanics. The thesis goes that the world has a beginning in time and is also limited with respect to space. The antithesis goes that the world has no beginning and no limits in space. That is, it is infinite with respect to both time and space. And as I said, in order to do things like Newtonian kinematics, we need clocks and a coordinate system. By imposing absolute time and absolute space, Newton could attain these frameworks that can be mapped onto the so-called real world by meaningful time and space measurements via clocks and coordinate systems. Essentially, Newtonian mechanics is embodied in the worldview of the thesis aspect of Kant's first antinomy regarding space and time. This is all to say, nevertheless, the fact that Newton was able to formulate a thoroughly adequate foundation for the mechanics of macroscopic bodies by introducing these two concepts of absolute space and absolute time is regarded as an outstanding stroke of genius, and deservingly so. We are reminded by the antithesis of Kant's first mathematical antinomy, however, that there is another side to the metaphysical coin that is still amenable to critical reason. One can conduct the simple thought experiment of, what if the velocity of all physical and chemical processes in the universe suddenly doubled simultaneously? Since our brains operate upon these physical and chemical processes, and therefore our mental experiences are predicated upon them as well, would we experience time differently, or would we even be able to be aware at all of such a shift? Thus, the notion of absolute time can be undermined. Furthermore, Albert Michelson and Edward Morley reasoned about measuring the motion of the Earth against the supposed luminiferous ether and yielded a negative result that was the first strong evidence against the existence of the ether. The luminiferous ether is basically once removed from the absolute space, so the Michelson-Morley experiment thus undermines the notion of absolute space. Indeed, Newtonian mechanics would struggle with reference frames that aren't moving in uniform rectilinear motion, or essentially non-inertial reference frames, such as accounting the forces experienced in a spinning room. The workaround amounts to attributing missing or fictitious forces as results derived from the acceleration of our reference frame with respect to the absolute frame, with the big examples of such fictitious forces for Newton being the centrifugal force and the Coriolis force. And everyone, of course, falls out of the womb with the mathematical understanding of physics that there is no centrifugal force, but it's rather centripetal force or a centripetal force. I once had a substitute teacher who pronounced it that way, centripetal. So it's rather centripetal force than centrifugal force, which is at play when you're perhaps centrifuging something. And a little aside, when I was in grad school, I was in cellular biology experimental lab, not very heavy on the computational side for like day in, day out sort of work. So everyone would be doing their various experiments, working in and out of the vent fume hoods, be pipetting stuff. And one of the bottlenecks in everyone's procedures would be the centrifuges. And even though you would maybe be spinning a few tubes at a time for a few minutes, if people are doing experiments at the same time, we would have to be working in on, right, like at the gym where you're working in on the different machines, you're working in on the centrifuge with other people in the lab. And anyways, the machine is called a centrifuge, but it's centripetal force. And indeed, when you have the tube with, let's say, your cellular proteins suspended in the media, you would put it in the centrifuge and spin it down for a few minutes, and then there would be the pellet of all your cellular material at the bottom. And I guess that would be due to the centripetal force pushing the liquid to the top end of the tube and the cellular media then ending up at the bottom because it's heavier, so it would have required a stronger centripetal force in order to not keep that suspended in the media. Anyways, but it is perhaps more advisable in cases involving centripetal or centrifugal phenomena than to say that accelerated motion is taking place not with respect to what is being centrifuged, but instead with respect to the remaining masses of the universe. It is the remaining masses of the universe rather than a cosmic ether corresponding to absolute space that is the cause of the centrifugal forces. This is experimentally very difficult to directly interrogate, however. After all, how would one cause a remainder of masses in the universe to simply vanish? The path forward is what necessitates differential geometry and, in general, a robust mathematical framework for characterizing manifolds, and this includes abandoning Euclidean geometry along the way. Einstein's fundamental idea in general relativity is to determine the metric of the space-time continuum by means of the distribution and velocity of matter in such a way that in a frame of reference relative to which the matter is in accelerated motion, then the inertial forces result automatically. This non-Euclidean metric of the space-time continuum being determined by the distribution and velocities of the material bodies in the universe is the geodesic, that is, the line of stationary length due to a light ray upon which no electromagnetic forces act. In other words, in Einstein's general relativity, the curvature of space-time causes frames to be locally inertial but globally non-inertial. Due to the non-Euclidean geometry of curved space-time, there are no global inertial reference frames in general relativity. More specifically, the fictitious force which occurs in general relativity is the force of gravity itself. Gravity is in this way inherently the result of the curvature of space-time. Interestingly enough, the same centrifugal forces would arise due to Einstein's general relativity whether the Earth is considered to turn on its axis within the rest of the universe or the rest of the universe to be rotating about the axis of the Earth. And hence, the original conflict between Ptolemy and Copernicus's views vanishes. So to recap, from Ptolemy to Copernicus, the reference frame or implicit coordinate system of the solar system was shifted from having the Earth at the center to having the Sun at the center, and this is the Copernican revolution. Einstein, however, used differential geometry to get rid of the necessity of an absolute coordinate system altogether to compute relativistic effects. Now, Einstein himself, within a few years of his initial publication of the Einstein field equations, proposed tests or experiments whose results would be predictably different according to general relativity than according to old physics. First, based upon conventional telescope data available at the time, the precession of the perihelion of Mercury, or the drifting of the point of closest approach of Mercury during its orbit around the Sun. The largest cause quantitatively of the perihelion precession of Mercury is the total combined gravitational tug due to the other bodies in the solar system. Additionally, the oblateness of the Sun itself contributing to the perihelion precession of Mercury is indeed at play and is a non-relativistic force. However, its contribution distribution is much less significant. Appropriate solutions of Einstein's field equation with relevant parameters successfully quantitatively agreed with conventional telescope data then to explain the 43 arcsecond advance of Mercury's perihelion. Second, general relativity provides a more accurate calculation for gravitational lensing. In the case of light grazing the surface of the sun, the calculated angular deflection of light from a star seen from behind the sun during a solar eclipse is on the scale of 2 times more deflection than otherwise predicted by calculations using the Newtonian theory of gravity. Now get out your eclipse glasses because this is the famous Eddington experiment. And finally, we have the gravitational redshift of light, or the change in the time metric caused by gravitation causing spectral lines originating in a strong gravitational field, for example due to the sun, to be very slightly shifted to the red when compared to an outside observer with spectral lines generated in their own system. Now, a key takeaway for me here is the observability, measurability, repeatability, and falsifiability of these tests. Nevertheless, these are successful tests, but their results do not constitute full quantitative proof or verification of general relativity. In short, the physics of the 4 fundamental forces, including gravity, pervade the universe, and quantum theory has turned out so far to be very accurate microscopically. Gravity is so weak at that scale, however, that it is basically ignored by quantum theory. Conversely, one intuitively expects that the accuracy of quantum theory microscopically would average out, quote unquote, so that quantum effects could be quantitatively expressed in macroscopic phenomena. These are the problems we allude to when we speak of the term quantum gravity these days, and this is how the situation of modern physics today is reminiscent of the age of Ptolemy's geocentric model. String theory, as a single theoretic framework describing the 4 fundamental interactions between subatomic particles, is decried by some as what amounts to Ptolemization, just adding complications and changing minor premises instead of transforming the basic framework in order to make progress. For as sharp and intelligent as Ed Witten clearly is, he has notoriously not proposed any experiments but has exclusively focused on a robust mathematical development of string theory. This is why some would say that physics right now is ripe for philosophy. Some mathematicians would say mathematics already has the tools to handle whatever a quantum gravity theory might look like. The philosophical opportunity is that the metaphysical framework of such a theory might entail radically abandoning space and/or time altogether. From the perspective of quantum theory, the perception of a particle determines its reality, and so metaphysically this entails the primacy of appearance over hard reality and attributing hard reality as indeterminate altogether. But hopefully now we can think about general relativity and we start to better appreciate the philosophical situation and the mathematical situation that is involved here. So along the lines of thinking of luminiferous ether as absolute space and astronauts in free fall, etc., differential geometry was what Einstein used to make his advancement with general relativity. Lilian Lieber, a Russian-American mathematician, once remarked that tensors are the facts of the universe. And a famous Chinese differential geometer and topologist, Xing-Shen Chern, once said about tensor calculus that, in our subject of differential geometry, where you talk about manifolds, one difficulty is that the geometry is described by coordinates, but the coordinates do not have meaning. They are allowed to undergo transformation. And in order to handle this kind of situation, an important tool is the so-called tensor analysis, or Ricci calculus, which was new to mathematicians. In mathematics, you have a function. You write down the function, you calculate, or you add, or you multiply, or you can differentiate. You have something very concrete. In geometry, the geometric situation is described by numbers, but you can change your numbers arbitrarily. So to handle this, you need the Ricci calculus. Indeed, one way to develop differential geometry is to start with congruence. For example, imagine a post office where there's a letter, say, with an address written on it. You could focus on just the zip code and consider how you or I or the postmaster general or anyone or anything could recognize the numbers in a zip code at all. There's variety in handwriting, of course, between individuals, and indeed the reproducibility of individuals' own handwriting of single characters even, of course, varies tremendously, and so on and so forth. So somehow these notions of different times that I've written the letter I are equivalent to each other, or that if I have two different styles of writing the number 1, that those are equivalent to each other, but that writing the letter I is not equivalent to writing the number 1. And similarly, when we have a symbol that looks like, say, a crude omega or one of those Jesus fish symbols, that is not equivalent to a symbol which looks like a letter R, or you could describe it as a hairpin curve. Somehow the difference between these different notions must be established. Some would say this involves ideas of path congruence, or the unique correlation of the function values corresponding to the paths to the arguments of those functions. One could also consider geometric congruence, that is, the coincidence or equivalence of a configuration up to differences in displacement, that is, transformations of coordinate systems. Equivalence, congruence, and invariance, often with respect to some sort of coordinate system and with respect to some transformation, are what are involved when we discuss what is an allowable representation or not. To continue to develop differential geometry, you could focus on generalizing single variable derivatives on a Euclidean plane as tangents from calculus. Along the way, you might have things like the Frenet equations, which are useful for imposing a coordinate system at points along a curve through the tangent normal and binormal. You could also prove that for continuous functions kappa of s representing curvature in terms of the real variable of arc length s, and the function tau of s representing torsion in terms of arc length, both defined on the interval capital I, where arc length s is greater than or equal to 0, but also less than or equal to some real value a, then there exists one and only one arc whose vector parametric representation is given by the function x of s, determined up to a direct congruent transformation with arc length s, whose curvature and torsion respectively are given by the functions kappa and tau. In other words, we can uniquely represent an arc by functions of its curvature and torsion parametrized by arc length, independent of the coordinate system except for the position of the curve in space. And the development just keeps going. Gauss was on the verge of the modern notion of Riemannian manifolds with his Theorem egregium, which we are actually going to get to hopefully in the future, chapter 4, section 46. Gregorio Ricci-Curbastro and his student Tullio Levi-Civita are credited with developing what is now known as tensor calculus, or tensor analysis, or Ricci calculus, which theory they published in 1900. Back in the day, Gregorio must have said something like, "My name is Gregorio Ricci-Curbastro, but everybody calls me Ricci." Levi-Civita would go further in 1917 with his work titled Notion of Parallelism in Any Variety and Consequent Geometric Specification of the Riemannian Curvature to define what we now know as the displacement of Levi-Civita, which also hopefully we will get to in the future chapter 7 on absolute differentiation and displacement in section 76. Indeed, differential geometry gives us the power to think about things like the 6-dimensional solution set of a polynomial of 4 complex variables as easily as we think of a 2-dimensional sphere in R3. However, this power, as you may appreciate already if you've been watching these videos, this power comes at the cost of being assembled from many layers of abstract structure stacked upon each other. So besides Ricci calculus, Ricci's namesake is also given to Richard S. Hamilton's Ricci flow, which has been famously used by Grigori Perelman to prove the Poincaré conjecture, specifically by using what he calls Ricci flow with surgery. And if you've made it this far and you're a real mathematician, then before I move on, please join me in reciting the statement of the Poincaré conjecture. Every 3-dimensional topological manifold which is closed, connected, and has trivial fundamental group is homeomorphic to the 3-dimensional sphere. So, to continue reading chapter 3 from Differential Geometry by Erwin Kreisig, we are in section 33, Special Tensors. Apart from the metric tensors G sub alpha beta and G superscript alpha beta, some other special tensors are of interest in the theory of surfaces. As was pointed out in the preceding sections, a sufficiently large number of any functions can be taken as components of a tensor with respect to a certain coordinate system on a surface, and the components of this tensor with respect to any other allowable coordinate system are then determined by means of the transformation laws for the coefficients of a mixed tensor of arbitrary order at a point P. We take the Kronecker symbols delta with a subscript alpha and a superscript beta as components of a mixed tensor of second order which which is called the mixed delta tensor. This tensor has the same components with respect to any other coordinate system. Indeed, let A over bar sub rho superscript sigma denote these components. Then A over bar sub rho superscript sigma equals Kronecker delta symbol subscript alpha superscript beta times partial u alpha partial u over bar rho times partial u over bar sigma partial u beta, which is equal to Kronecker delta sub rho with a superscript sigma on the Kronecker delta. The covariant epsilon tensor of second order is identified by epsilon sub 1 equals 0, epsilon sub 1 equals the square root of g, epsilon sub 2 equals the negative square root of g, and epsilon sub 2 equals 0. This tensor is skew symmetric. In consequence of the transformation laws for the coefficients of a covariant tensor of second order at a point P, we have that epsilon over bar sub mu nu is equal to epsilon sub alpha beta times partial u alpha partial u over bar mu times partial u beta partial u over bar nu. Or since epsilon 1 equals epsilon 2 equals 0, then epsilon over bar sub mu nu equals epsilon sub 1 times partial u1 partial u over bar mu times partial u2 partial u over bar nu plus epsilon sub 2 times partial u2 partial u over bar mu times partial u1 partial u over bar nu. That is, epsilon over bar sub mu nu equals the square root of g times the determinant, where in the first column we have derivatives of u1, where first we have the partial derivative of u1 in terms of u over bar mu, and then we have in the same column the partial derivative of u1 with respect to u over bar nu. And then in the second column, correspondingly, we have the partial derivatives with respect to u over bar mu and then u over bar mu for u2. Therefore, epsilon over bar 1 equals epsilon over bar 2 which equals 0, and epsilon over bar sub 1 equals the square root of g times partial u1 u2 partial u over bar 1 u over bar 2, which is equal to the square root of g over bar, and epsilon over bar 2 equals the negative square root of g times partial u1 u2 partial u over bar 1 u over bar 2, which is equal to the negative square root of g over bar. And you can refer back to 28.4, which is from Theorem 28.3, which states that for coordinates u1 and u2 undergoing an allowable transformation by u alpha given by the function u alpha in terms of u over bar 1 and u over bar 2 such that alpha is equal to 1 and 2, then g over bar is equal to capital D squared times g, and g is equal to capital D over bar squared times g over bar, where g over bar is the determinant of the first fundamental form with respect to the coordinates u over bar 1 and u over bar 2, and capital D over bar are the Jacobians of the coordinate transformation and of its inverse, respectively. The tensor epsilon superscript mu nu is equal to epsilon sub alpha beta times g superscript mu alpha times g superscript nu beta. This tensor is called the contravariant epsilon tensor of second order. Since epsilon sub 1 equal to epsilon sub 2 equals 0, we find that epsilon superscript mu nu equals the square root of g times the quantity g superscript mu 1 times g superscript nu 2 minus g superscript mu 2 times g superscript nu 1 closed quantity. And therefore, epsilon superscript 1 equal to epsilon superscript 2, which is equal to 0. Epsilon superscript 1 is equal to the square root of g times the quantity g superscript 1 times g superscript 2 minus the square of g superscript 1 closed quantity, and this is then equal to 1 over the square root of g, and this is due to the relation given by g star equivalent to g superscript 1 times g superscript 2 minus the square of g superscript 1 being equal to 1 over g, and similarly e superscript 2 is equal to the negative reciprocal of the square root of g. The contravariant epsilon tensor has therefore the components epsilon superscript 1 equals 0, epsilon superscript 1 equals the reciprocal of the square root of g, epsilon superscript 2 equals negative 1 over the square root of g, and epsilon superscript 2 equals 0. Furthermore, epsilon superscript alpha gamma times epsilon subscript beta gamma equals epsilon superscript alpha 1 times epsilon subscript beta 1 plus epsilon superscript alpha 2 times epsilon subscript beta 2, which is equal to either 0 when alpha does not equal beta or 1 when alpha does indeed equal beta. That is, epsilon superscript alpha gamma times epsilon subscript beta beta gamma is equal to the Kronecker delta with a subscript beta and then a superscript alpha. Similarly, epsilon superscript alpha gamma times epsilon sub gamma beta is equal to the negative Kronecker delta with a subscript beta and a superscript alpha. A tensor whose components are all zero is called a null tensor. If for a tensor all components with respect to a certain coordinate system vanish, the components of this tensor with respect to any allowable coordinate system vanish. This is an immediate consequence of the transformation laws for the coefficients of a mixed tensor of arbitrary order at a point P. Now we come to our first problem of the section, problem 33.1. Determine the components of the covariant epsilon tensor starting from the components of the contravariant epsilon tensor and using the contravariant epsilon tensor of second order. So from the contravariant epsilon tensor of second order, we obtain G sub mu tau times G sub gamma sigma times epsilon superscript mu nu equals epsilon sub alpha beta times G sub mu tau times G superscript mu alpha times G sub nu sigma times G superscript nu beta, which is equal to epsilon sub alpha beta times Kronecker delta sub tau with a superscript alpha times Kronecker delta with a subscript sigma and a superscript beta. That is, epsilon sub tau sigma is equal to epsilon superscript mu nu times G sub mu tau times G sub nu sigma. If we insert the components of the contravariant epsilon tensor into this previous relation for epsilon sub tau sigma, we find that epsilon sub tau sigma is equal to 1 over the square root of G, then times the quantity G sub 1 tau times G sub 2 sigma minus G sub 2 tau times G sub 1 sigma. Hence, epsilon 1 1 equals epsilon 2 2, which equals 0, and epsilon sub 1 2 equals the square root of G, and epsilon sub 2 1 equals the negative square root of G. Problem 33.2. Find a representation of the contravariant metric tensor in terms of the contravariant one and epsilon tensors. Using the relation epsilon superscript alpha gamma times epsilon sub beta gamma equal to Kronecker delta subscript beta with a superscript alpha, and the relation epsilon sub tau sigma equals epsilon superscript mu nu times G sub mu tau times G sub nu sigma from the answer of the previous problem, we obtain that epsilon superscript alpha gamma times epsilon superscript mu nu times G sub mu beta times G sub nu gamma times G superscript beta kappa equals a Kronecker delta with a subscript beta and a superscript alpha times G superscript beta kappa, which is equal to G superscript alpha kappa. In consequence of the conjugate relationship of the covariant and contravariant metric tensor, G sub alpha gamma times G superscript gamma beta equals the Kronecker delta with a subscript alpha and a superscript beta. We find from this the desired representation G superscript alpha kappa equals epsilon superscript alpha gamma times epsilon superscript kappa nu times G sub nu gamma. Problem 33.3. Find the associate mixed tensor of the covariant metric tensor. We have to raise a subscript of G sub alpha beta by means of the contravariant metric tensor. We thus obtain the conjugate relationship of the covariant and contravariant metric tensor. That is, the mixed delta tensor may be considered as the mixed metric tensor. Moving along, problem 33.4. Evaluate the following expressions. Kronecker delta sub alpha and then superscript alpha, and then we have Kronecker delta sub alpha superscript beta times Kronecker delta subscript beta superscript alpha, and then we have Kronecker delta symbol sub alpha superscript beta times Kronecker delta symbol sub beta superscript gamma times delta sub gamma superscript alpha. And for all of these, since contraction has to be carried out with respect to all indices, the result is a scalar, namely in each case the number 2. Section 34. Normal to a surface. As was pointed out in section 26, which was on curves on a surface and the tangent plane to a surface, to any point of a surface capital S given by the vector parametric representation x in terms of u1 and u2, we can associate the two vectors x1 equivalent to partial x partial u1 and x2 which is equivalent to partial x partial u2. At any regular point capital P of capital S, these vectors are linearly independent and are tangent tangent to the coordinate curves through the point capital P. They span the tangent plane capital E of P to capital S at capital P. The unit vector n, which is orthogonal to those vectors and whose sense is such that x1, x2, n in this order form a right-handed triple of vectors, is called the unit normal vector to the surface capital S at the point capital P. And this is shown in figure 40, which hopefully is on the screen now. Obviously, n is equal to x1 cross product with x2 over the magnitude of the cross product of x1 with x2, which is then equal to the cross product of x1 with x2 over the positive square root of g, where the denominator of the positive square root of g follows from the fact that the magnitude of the cross product of x1 and x2, then taking that magnitude squared, is equal to the square of the magnitude of x1 times the square of the magnitude of x2 times the square of sine of alpha, where alpha is the angle between the vectors x1 and x2, and this is then equal to g sub 1 times g sub 2 times quantity 1 minus cosine squared of alpha, which is then equivalent to g sub 1 times g sub 2 minus the square of the dot product of x1 and x2. The straight line through capital P in the direction of n is called the normal to the surface capital S at the point capital P. To any regular point of capital S, there now corresponds a trihedron consisting of the vectors x1, x2, and n. In contrast to the trihedron of a curve, which consists of 3 orthogonal unit vectors, the trihedron of a surface contains, in general, only one unit vector, namely n, since the magnitude of x1 equals the square root of g11 and the magnitude of x2 is equal to the square root of g22, as follows from the relation that the vector x sub alpha dot product with the vector x sub beta is equal to g sub alpha beta. And all 3 of these vectors are mutually orthogonal if and only if the dot product of x1 and x2 is equal to g sub 1, 2, which is equal to 0. The sense of the unit normal vector n depends on the choice of the coordinates on the surface capital S. After the coordinate transformation given by u1 equals u over bar 2 and u2 is equal to u over bar 1, the sense of n will change, since the Jacobian of this transformation has the value -1. A transformation whose Jacobian is positive preserves the sense of n, while n changes its sense under a transformation whose Jacobian is negative. And now we arrive at an example. The unit normal vector to the sphere given by the relation where x1 is equal to r cosine u2 times cosine of u1, and then in x2 is equal to r cosine u2 times sine u1, and in x3 is equal to r sine u2, where u1 is greater than or equal to 0 while less than 2 pi, and u2 is greater than or equal to negative pi over 2 and less than or equal to pi over 2. And so the unit normal vector to this sphere is directed away from the interior of said sphere. When, for example, the transformation given by u1 equal to negative u over bar 1 and u2 equal to u over bar 2, when that transformation is imposed, the sense of the normal vector changes. Now, a surface is said to be orientable if the positive normal direction, when given at an arbitrary point capital P, can be continued to the whole surface in a unique way. That is, if there does not exist a closed curve capital C through capital P, which is of such a type that, when displacing continuously the given positive normal direction from capital P along capital C and back to capital P, one obtains in the end a positive normal direction at capital P opposite to the given one. A sufficiently small portion of a surface is always orientable. We notice that this may not hold in the large. There are non-orientable surfaces. A well-known example of a surface of this type is the Möbius strip, which there's a depiction of in figure 41. When a given positive normal direction at capital P naught is continuously displaced along capital C, the direction obtained upon returning to capital P naught is opposite to the originally given one. And so actually I thought that to make that more clear, I would create a Möbius strip for you guys. All right, so first you get a piece of paper here and you get 2 different colors and you get your ruler, and we're just going to draw a straight line with one of the colors on one side. And we're going to repeat this same exact place, but on the back of the page. And then we're going to cut this out. So now, on one side of the piece of paper, we clearly have a blue line, and on the other side, we clearly have a red line, unless you're colorblind. And so now we're going to grab the tape, and to make our Möbius strip, I use 2 pieces of tape. And we're just going to take the strip, and we're going to wrap it around, and we're going to tape like so. Okay, and then the same on the other side. All right. And now we've got a Möbius strip. So now we have our Möbius strip, and we know this because if I start right here, it'll hopefully focus. We start here, and we keep moving along here. Remember, the blue was on one side and red was on the other, and we keep moving it along. We just keep sliding the tape around. Eventually, oh, what do you know? Keep twisting. Now suddenly the line is red. We're on the other side of the page. Oh, now we're back. Now we're in the blue again. And back to red. So it's impossible to orient a Möbius strip, as you just saw. I don't know if me reading that paragraph was more clear to you, or if making a Möbius strip and seeing it was more helpful. We are on YouTube. You never know. Let me know in the comments down below. Moving on, the allowable representations of a portion of a surface may be divided into 2 classes corresponding to the different possible orientations. Obviously, any 2 representations belong to the same class if one of them can be transformed into the other by means of a transformation whose Jacobian is positive. And now we are in section 35, measurement of lengths and angles in a surface. And actually, I think that going back to the reacting to differential geometry hater comments, the only hater was Scotty Chen. I love all your guys' comments, including Scotty Chen's. But speaking of Scotty Chen, I think part of his criticism of me was that in the earlier first fundamental form section, earlier in this chapter, it should have gone into measuring lengths and angles in a surface right away. And so I think it really just comes down to the order of how this book was laid out. That was part of Scotty Chen's criticism. So now we're getting to it in section 35 now, Scotty Chen. I'm not the one who organized this book, you know. But anyways, we have mentioned already like I said, we have mentioned already in section 27, which is on the first fundamental form and also the concept of Riemannian geometry, and it established what we know as the Einstein summation convention. We mentioned already in that section that the first fundamental form enables us to measure lengths, angles, and areas in a surface. Let capital C given by u1, which is equal to the function u1 of parameter t, and u2, which is given by the function u2 of the same parameter t, be a curve on a surface capital S given by the parametric representation x of u1 and u2, as per section 26, which was on curves on a surface and the tangent plane to a surface. Then, according to 9.1, which was the formula for the length of an arc capital C, which was originally given in terms of the parameter t, which is greater than or equal to a and less than or equal to b, and t is just a Euclidean real single variable. It's a subset of the real numbers, of course, that we're working with on the interval from a to b. So the length of this arc capital C given originally in terms of t, this length of an arc, which we will call S, which is independent of the special choice of the allowable parametric representation, S is given by the integral from a to b of the square root of the derivative of that parametric representation's first derivative in terms of t dot product with itself. So you could say x prime dot product with x prime and then take the square root of that. That is what you're integrating from a to b in terms of t, so dt. So once again, s equals the integral from a to b of the square root of x prime dot x prime. So according to this, the length of an arc capital C bounded by the points corresponding to the values t equals t naught and t equals t sub 1 is given by the integral s equals the integral from t naught to t1 of the square root of x prime dot with x prime dt is equal to the integral from t naught to t1 of the square root of the dot product of x sub alpha times u superscript alpha prime with x sub beta times u superscript beta prime, and then this square root of a dot product is then dt. And so that is in consequence of x sub alpha dot with x sub beta equal to g sub alpha beta, we have that s equals the integral from t naught to t1 of the square root of g sub alpha beta times u superscript alpha prime times u superscript beta prime, then dt, where primes, of course, as usual, denote derivatives with respect to t. We consider now the measurement of angles in a surface. The scalar product of two vectors in the surface capital S, namely a equal to a superscript alpha times x sub alpha and b equal to b superscript beta times x sub beta, which are bound at the same point capital P, is given by the expression a dot b equal to the quantity a superscript 1 times x sub 1 plus a superscript 2 times x sub 2 closed quantity dot product with quantity b superscript 1 times x sub 1 plus b superscript 2 times x sub 2 closed quantity, or a dot b, or the scalar product of a and b, is equal to g sub alpha beta times a superscript alpha times b superscript beta, as per the relation x sub alpha dot x sub beta equal to g sub alpha beta. So in consequence of the contravariant components of a vector v in a surface capital S at capital P obtained by the covariant ones, and the conjugate relationship of the covariant and contravariant metric tensor, we find g sub alpha beta times a superscript alpha times b superscript beta equals g sub alpha beta times g superscript alpha gamma times a sub gamma times b superscript beta, which is equal to the Kronecker delta with a subscript beta and a superscript gamma times a sub gamma times b superscript beta, which is equal to a sub beta times b superscript beta, which is equal to g superscript alpha beta times a sub beta times b sub alpha. Hence, we may write that the dot product of a and b is equal to a sub beta times b superscript beta, or the dot product of a and b is equal to g superscript alpha beta times a sub alpha times b sub beta. The vector a therefore has the length given by magnitude of a equal to the square root of the dot product of a with itself, which is equal to the square root of g sub alpha beta times a superscript alpha times a superscript beta, which is equal to the square root of a sub alpha times a superscript alpha, which is equal to the square root of g superscript alpha beta times a sub alpha times a sub beta. We denote by gamma the angle between the vectors a and b. Then, according to from the preliminaries chapter, cosine alpha equals the dot product of vectors, let's say c and d, over the product of their magnitudes is then equal to c dot d over the square root of c dot c, then times the square root of d dot d. Due to this, we then have that the cosine of gamma is equal to, in the numerator, the dot product of a with b, then over in the denominator, the product of the magnitudes of a and b. This fraction is equal to, in the numerator, g sub alpha beta times a superscript alpha times b superscript beta, all over then in the denominator, the square root of g sub mu nu times a superscript mu times a superscript nu, times then another square root, which is of g sub sigma tau times b superscript sigma times b superscript tau. This is then equal to, in the numerator, a sub alpha times b superscript alpha, all over the product of two square roots, the first being a sub beta times a superscript beta, and the second square root being b sub gamma times b superscript gamma. And this is all finally equal to, in the numerator, g superscript alpha beta times a sub alpha times b sub beta, all over the product of two square roots, the first being g superscript mu nu times a sub mu times a sub nu, and then the second square root being of g superscript sigma tau times b sub sigma b sub tau. We now consider two curves. Capital C given by u alpha, which is equal to the function h alpha in terms of the parameter t, and c star, which is given by u alpha equal to the function h alpha star in terms of t as well, where alpha can be 1 or 2. On a surface capital S, these two curves are on a surface capital S, which is given by the vector parametric representation x of u1, u2, which intersect these two curves, that is, they intersect at a point capital P of capital S. By definition, the angle gamma of intersection is the angle between the vector v, which is equal to d dt of x of, in the first entry, h1 of t, and in the second entry, h2 of t, which is then equal to x sub alpha times h superscript alpha prime. This vector v, which is tangent to capital C at the point capital P, and the vector v star, which similarly is equal to d dt of x of, in the first entry, h1 star of t, and in the second entry, h2 star of t. This is then equal to x sub beta times h superscript beta star prime, which is tangent to capital C star at the point capital P. According to the cosine of the angle alpha between the vectors A and B on a surface, we therefore obtain that cosine of gamma is equal to a fraction with the numerator of the dot product of V with V star, and in the denominator the product of the magnitudes of V and V star respectively. This fraction is then equal to another fraction with the numerator of G sub alpha beta times H superscript alpha prime times H superscript beta star prime, all over a denominator which is the product of two square roots, the first being g sub mu nu times h superscript mu prime times h superscript nu prime, and the other square root being g sub sigma tau times h superscript sigma star prime times h superscript tau star prime, etc. Hence, capital C and capital C star intersect orthogonally if and only if at the point capital P, g sub alpha beta times h superscript alpha prime times h superscript beta star prime equals 0. The vectors x1 and x2 are tangent to the respective coordinate curves u2, which is equal to a constant, and u1, which is equal to a constant. Denoting by omega the angle of intersection of these curves, we have that the cosine of omega is equal to a fraction with the numerator of the dot product of x1 and x2 and the denominator of the product of the magnitudes of x1 and x2 respectively, equaling the fraction with the numerator of g sub 1, 2 and the denominator of the square root of g sub 1, 1 times g sub 2, 2. An allowable coordinate system on a surface capital S is said to be orthogonal if, at any point of capital S, the surface, the coordinate curves intersect orthogonally. From the formula for the cosine of omega, we obtain the following important theorem. Theorem 35.1. A coordinate system on a surface capital S is orthogonal if and only if, at any point of capital S, g sub 1, 2 is equal to 0. In many connections, the choice of orthogonal coordinates is of great advantage since the formulae becomes simpler if such a coordinate system has been chosen. Examples of orthogonal coordinates have occurred already in the previous section, section 27 on the first fundamental form. Applications of these coordinates will follow. For further purposes, we shall need the formula sine of gamma, which is equal to the square root of g times a fraction where in the numerator we have the magnitude of a superscript 1 times b superscript 2 minus a superscript 2 times b superscript 1, and then in the denominator the product of two square roots, the first being g sub alpha beta times a superscript alpha times a superscript beta, and the second square root being of g subscript mu nu times b superscript mu times b superscript nu, where gamma is greater than or equal to 0 and less than or equal to pi, and this relation for the sine of gamma can immediately be obtained from the relation for the cosine of the angle alpha between the vectors a and b on the surface S by using the relation sine squared of gamma is equal to 1 minus cosine squared of gamma. Now, since a superscript 1 times b superscript 2 minus a superscript 2 times b superscript 1 is equal to g superscript 1 alpha times a subscript alpha times g superscript 2 beta times b subscript beta minus g superscript 2 alpha times a sub alpha times g superscript 1 beta times b sub beta equals then finally 1 over g times the quantity a sub 1 times b sub 2 minus a sub 2 times b sub 1 closed quantity. We finally then obtain from the previous relation for sine of gamma that the sine of gamma is similarly equal to a fraction where we have a numerator equal to the magnitude of a sub 1 times b sub 2 minus a sub 2 times b sub 1, and then in the denominator, the product of three square roots, the first being just the square root of g, then the second square root being g superscript alpha beta times a sub alpha times a sub beta, and then the third square root in the denominator being g superscript mu nu times b sub mu times b sub nu, where for this relation, gamma is greater than or equal to 0 and less than or equal to pi. The angle gamma, which is greater than or equal to 0 and less than or equal to pi, is uniquely determined by its cosine, but not by its sine. So if gamma is greater than or equal to 0 and less than or equal to pi, then the sine of gamma is greater than or equal to 0. That is, the right-hand sides of the formula for the sine of gamma, where the numerator had superscript contravariant indices, and the relation for sine of gamma where the numerator had subscript covariant indices, the right-hand sides of these relations must be positive. Problem 35.1. Introduce orthogonal coordinates on a general helicoid capital S such that the helices and their orthogonal trajectories on capital S are coordinate curves, and refer back to problem 28.5. In the answer to problem 28.5, the curves u1 equals a constant are helices on the helicoid capital S. We determine the orthogonal trajectories of those helices by introducing new orthogonal coordinates u superscript 1 star, which is equal to u1, and u superscript 2 star, which is equal to capital F of u1 and u2. To the coordinates u1 and u2, there corresponds the first fundamental form, which is given by ds squared equals the quantity 1 plus capital G prime squared, closed quantity, times the square of du1 plus 2 times c times capital G prime times du1 times du2 plus the quantity u1 squared plus c squared, closed quantity, times the square of du2. Or this first fundamental form is also then ds squared equals the quantity 1 plus the fraction with a numerator of u1 squared times capital G prime squared, and then in the denominator u1 squared plus c squared, and then close that quantity, but then multiply it by du1 squared, and then we have that plus the quantity u1 squared plus c squared, closed quantity, times then the quantity, which shortly after I read what the contents of this quantity are, this last quantity itself will be squared, so I'm referring to thus contained within that quantity a fraction with a numerator c times capital G prime and then a denominator u1 squared plus c squared. Then that fraction is times du1, and the resulting product is then plus du2. That encloses the final quantity, which, like I said, is then squared. And so we set, in order to clean things up here a little bit, we set the fraction with a numerator c times capital G prime and the denominator u1 squared plus c squared, then times du1 plus du2. We set that equal to eta times du2 star, where eta is a constant. That is, by setting the above expression equal to eta times du2 star, we make the transformation where u1 star is equal to u1 and then u2 star is equal to 1 over eta times the quantity c times the integral of a fraction with a numerator of capital G prime and a denominator of u1 squared plus c squared, then that times du1 plus u squared, where eta is non-zero. Then we have that ds squared is equal to the quantity 1 plus the fraction of a numerator u1 star squared times capital G prime squared and a denominator u1 star squared plus c squared, closed quantity, times the square of du1 star plus eta squared times the quantity u1 star squared plus c squared, closed quantity, times du2 star squared, where a prime denotes the derivative with respect to u1 star. The coordinates u1 star and u2 star are orthogonal, as per Theorem 35.1, which we just went over, saying that a coordinate system on a surface capital S is orthogonal if and only if at any point of capital S g sub 1, 2 is equal to 0. So the curves u1 star equal to a constant are the helices under consideration, and the curves u2 star equal to a constant are the orthogonal trajectories of those helices. All right, section 36, area. The definition of surface area resembles that of the length of an arc. When introducing the concept of the length, we approximated the given arc by a broken line of chords. Similarly, we have now to approximate the given portion of a surface by small portions of planes. The method used will not be exactly analogous to that of section 9, which was on the arc length. The reasons for the difference in the two investigations will be explained in a future section, section 37. Let x of u1, u2 be an allowable representation of a curved surface capital S. We consider a portion capital H of capital S, whose orthogonal projection capital T in the x1, x2 plane is 1-to-1, and whose normal at any point of capital H, the portion, does not make a right angle with the x3 axis. We denote by capital H over bar the image of capital H under the projection capital T. The boundary capital C of capital H is assumed to be composed of finitely many arcs of curves. Then the image capital C over bar of capital C in the x1, x2 plane has the same property, and consequently the area of capital H over bar exists. We subdivide capital H over bar into finitely many portions lowercase h over bar sub n so that the area of any lowercase h over bar sub n exists. Let h sub n be the inverse image of h over bar sub n. The subdivision of capital H over bar corresponds to a subdivision of capital H into finitely many portions of lowercase h sub n. Let capital P sub n be an arbitrary point of lowercase h sub n. We denote by lowercase h star sub n the image of h sub n with respect to a parallel projection of lowercase h sub n into the tangent plane to capital H at capital P sub n. The projecting lines are assumed to be parallel to the x2 axis. The projecting lines are assumed to be parallel to the x3 axis as shown in figure 42. The smaller lowercase h sub n, that is, the smaller the maximum distance of any 2 points of lowercase h sub n, the less lowercase h star sub n will differ from lowercase h sub n. Hence, we may approximate the area capital A of h sub n by the area capital A of h star sub n of the plane portion h star sub n, which area is known. We denote by alpha of capital P sub n the angle between the normal to capital H at capital P sub n and the x3 axis. Let capital A of h over bar sub n be the area of h over bar sub n. Then capital A of h star sub n equals a fraction with a numerator of capital A of h over bar sub n and a denominator of the cosine of alpha of capital P of n, where alpha of P of n is not equal to pi over 2. When developing the determinant occurring in the tangent plane capital E of capital P on a surface of interest capital S at the point capital P, where x is the position vector of P, y is on the plane E of P, and x1 and x2 are tangential to the coordinate curves passing through the point P on the surface under consideration, we have the determinant where in the first column we have the vector y minus the vector x, and then in the second column we have the vector x1, and then in the third and last column we have the vector x2. This determinant is equal to 0. So when developing the determinant in that relation, by its first column we find that the sum on the index I from 1 to 3 of capital D sub I times y sub I minus x sub I equals 0, where capital D sub 1 is equal to partial x2, x3, partial u1, u2, capital D sub 2 is equal to partial x3, x1, partial u1, u2, and capital D sub 3 is equal to partial x1, x2, partial u1, u2, and partial xi, xk, partial u1, u2 is equivalent to the determinant where the first column is the partial derivatives in terms of u1 of xi and then xk, and then in the second column it's partial derivatives in terms of u2 of xi and then xk. Therefore, the cosine of alpha of capital P sub n is equal to a fraction of numerator capital D sub 3 and a denominator which is the square root of the sum on the index I from 1 to 3 of D sub I squared. This expression holds for one of the two possible directions of the normal to capital H. If we direct this normal so that alpha of P sub n is less than pi over 2, then cosine of alpha of P sub n is positive, greater than 0, and cosine of alpha of capital P sub n is equal to then a fraction fraction where the numerator is the magnitude of d sub 3 over a denominator of the square root of the sum on the index I from 1 to 3 of d sub I squared. This is then equal to the magnitude of d sub 3 over the square root of g, which is due to two things. The first being that in order that the Jacobian matrix of a curve be of rank 2 or full rank in 2 dimensions essentially, the sum of the squares of the second order determinants contained in that Jacobian matrix must be positive. And then the second thing is that this sum is the discriminant g of the first fundamental form. Let capital N be the number of portions lowercase h sub n. We define the area of capital H by the expression capital A of capital H equal to the limit where capital N tends to infinity of the sum on the index n from 1 to capital N of capital A of lowercase h star sub n, where the limit process has to be carried out in such a manner that the maximum distance between any 2 points of any h star sub n ultimately becomes arbitrarily small. Using the formula for the area of a portion of a surface and the relation for cosine of alpha of capital P sub n, we obtain from the previous limit of a sum representation that capital A of capital H is equal to the limit where capital N tends to infinity of the sum on index n from 1 to capital N of first the fraction with the numerator square root of g of p over bar sub n closed square root and the denominator of the magnitude of capital D sub 3 of capital P over bar sub n. And then this fraction within the summand is times capital A of lowercase h over bar sub n. And in this relation, capital P over bar sub n is the image of capital P sub n with respect to the above projection capital T. We will prove that the limit of the aforementioned representation of capital A of capital H exists and is given by the integral capital A of capital H is equal to a double integral on a domain capital H over bar of fraction with a numerator square root of g over a denominator of the magnitude of capital D sub 3, and this double integral is in terms of dx1 dx2. Clearly, when introducing the variables u1, u2 then, by the general law of transformation of double integrals, this previous double integral becomes capital A of capital H equal to the double integral on capital U, which is the domain in the u1, u2 plane corresponding to capital H. This double integral is of first the fraction numerator square root of g over the magnitude of capital D sub 3 and then times the magnitude of capital D sub 3, and this double integral is in terms of du1 du2, which this double integral then simplifies to the double integral on capital U of simply the square root of g du1 du2. Furthermore, this double integral is invariant with respect to any allowable coordinate transformation. Indeed, when imposing such a transformation, the integrand of this double integral is multiplied by the absolute value of the corresponding Jacobian, while the square root of g is multiplied by the absolute value of the Jacobian corresponding to the inverse transformation. And see the transformation law stated in the previous section. The product of these two Jacobians has the value 1, which can be seen from problem 28.4 again in a previous section. Moreover, when applying this double integral to a portion of a plane, this formula becomes identical with the elementary formula by which plane areas are defined. We will now prove the above statement. Since the representation of capital H is allowable, the function capital Q equivalent to the fraction with the numerator of square root of g and the denominator of the magnitude of capital D3 is continuous and bounded in the domain under consideration. Hence, by applying to the relation for capital H as a double integral, the mean value theorem on surface integrals, we obtain that capital A of capital H is equal to the sum on the index n from 1 to capital N of the double integral on h over bar sub n of capital Q dx1 dx2, which is equal to the sum on the index n from 1 to capital N of capital Q of capital P over bar prime sub n times capital A of lowercase h over bar sub n, where capital P over bar prime sub n is a point of lowercase h over bar sub n. Capital Q is uniformly continuous in the domain under consideration. Therefore, a number epsilon which is greater than 0 being given, we can make all h over bar sub n so small that the variation of capital Q on any h over bar n becomes smaller than or equal to epsilon. Consequently, we can estimate the difference d, which is equivalent to the sum on the index n from 1 to capital N of the quantity capital Q of capital P over bar prime sub n minus capital Q of capital P over bar sub n closed quantity times capital A of lowercase h over bar sub n of the relation for capital A of capital H as a double integral given previously, and the finite sum occurring in its other formulation in the following manner, we can estimate the difference in the following manner, where the magnitude of d sub n is less than or equal to the sum on the index n from 1 to capital N of quantity capital Q of capital P over bar prime sub n minus capital Q of capital P over bar sub n closed quantity times capital A of lowercase h over bar sub n, which is less than or equal to epsilon times the sum on the index n from 1 to capital N of capital A of lowercase h over bar sub n, which is then equal to just epsilon times capital A of capital H over bar. Hence, the limit occurring in the formulation of capital A of capital H as a limit tending to infinity of a sum, this limit exists and is given by capital A of capital H as a double integral. We sum up our results as follows. Definition 36.1. The area capital A of capital H of a portion capital H of a surface capital S given by a vector parametric representation x of u1, u2 is defined by the double integral capital A of capital H of the double integral on capital U of square root of g, then du1 du2, where in this integral capital U denotes the domain in the u1 u2 plane corresponding to capital H. The expression d capital A equals square root of g du1 du2 is called the element of area of capital H. The element of area of capital H can be geometrically interpreted as the area of an infinitesimal parallelogram whose sides are the vectors x sub 1 du1 and x sub 2 du2. So a review from analysis, infinitesimal means a quantity that is closer to zero than what any standard non-zero real number is, but not zero itself. Indeed, from the definition of a vector product, it follows that the parallelogram has the area given by the magnitude of the cross product of x sub 1 du1 with x sub 2 du2, which is equal to the magnitude of x1 cross x2, then du1 du2. Using Lagrange's identity, which is given in the preliminary section, we find that the magnitude squared of the cross product of x1 and x2 is equal to the dot product of the cross product of x1 and x2 with itself, which is then equal to the dot product of x1 with itself times the dot product of x2 with itself, then minus the square of the dot product of x1 with x2, and we refer to this as g. From this, the result follows. So in the previous definition for the area capital A of a portion capital H in terms of a double integral, the square root of g has a positive sign. Therefore, capital A of capital H is positive. In addition to the area as defined above, one may consider also signed areas of portions of surfaces. In this case, the area corresponding to one of the two possible orientations is defined by the double integral for the area capital A of capital H of a portion capital H of a surface capital S, while the area corresponding to the other orientation is defined by negative capital A of capital H. In consequence of the investigations contained in this and the preceding section, we have the following result. The coefficients g sub alpha beta of the first fundamental form enable us to measure lengths, angles, and areas in a surface. By the tensor g sub alpha beta, the metric in a surface is thus completely determined. This is the justification of the name metric tensor. Now an example. In the case of the sphere given by x1 equal to r cosine u2 cosine u1, x2 equal to r cosine u2 sine u1, x3 equal to r sine u2, where u1 is greater than or equal to 0 and less than 2 pi, and u2 is greater than or equal to negative pi over 2 and less than or equal to pi over 2, we have that g sub 1, 1 is equal to r squared times cosine squared of u2, g sub 1, 2 is equal to 0, g sub 2, 2 is equal to r squared, and d capital A is equal to r squared cosine u2 du1 du2. The total area of the sphere is therefore 4 pi r squared. A further simple example is included in a future section 43. And now, section 37, remarks on the definition of area. It is natural to compare the investigations which led to the integrals for arc length and the area of a portion of a surface, by which the arc length and the area respectively are defined. The introduction of the concept of area in a manner completely analogous to that of section 9 for arc length would require the consideration of polyhedra whose vertices lie on the portion of the surface under consideration. But unless certain restrictions are imposed, this method would not lead to a uniquely determined limit, as can be seen by the following simple example. We consider the cylinder capital Z given by x1 squared plus x2 squared equals 1, and undertake to find the area of the portion capital H of capital Z defined by x3 greater than or equal to 0, but also x3 being less than or equal to 1. We construct a portion capital P of a polyhedron consisting of congruent triangles capital D in the following manner. We take on capital H equidistant circles parallel to the x1, x2 plane defined by x3 equals 0 or 1 over k or 2 over k, etc. through k minus 1 over k and then finally k over k. Obviously, the circles x3 equals 0 and x3 equals 1 form the boundary of capital H. We divide each of these circles into n congruent arcs so that the endpoints of the arcs on one circle lie over the midpoints of the arcs of the preceding circle, as can be seen in figure 43. When joining the endpoints of the arcs on any circle, we obtain a regular n-sided polygon. We now join every side of capital S of these polygons with those two vertices of the adjacent polygons, which are at a minimum distance from capital S. In this manner, we obtain the portion capital P of a polyhedron consisting of two kn congruent isosceles triangles capital D, as shown in figure 43. The sides of the above polygons have the length 2 sine of pi over n, and according to the theorem of Pythagoras, the altitude of each triangle capital D is thus a equal to the square root of the quantity 1 over k squared plus the quantity 1 minus cosine pi over n, closed quantity squared, which this square root is then equal to the square root of the quantity 1 over k squared plus 4 times sine to the 4th power of pi over 2n. The area of capital P therefore becomes capital A of k and n equal to 2n times sine of pi over n times the square root of the quantity 1 plus 4 times k squared times sine to the 4th of pi over 2n closed quantity. The limit of this expression depends on the manner in which k and n tend to infinity. First of all, if n is kept fixed, then the limit as k approaches infinity of capital A of k and n is equal to infinity. The reason for this fact is simple. The angle between each triangle capital D and the tangent plane to the cylinder tends to pi over 2. The area of each triangle tends to a finite value different from 0, and the number of triangles increases arbitrarily. In this case, capital P is, so to speak, pleated. Let now both k and n increase arbitrarily so that always k is equal to n squared. Let now both k and n increase arbitrarily so that always k equals n to the s. Then if s equals 1, capital A of k and n tends to 2 pi. If s equals 2, capital A of k and n tends to 2 pi times the square root of the quantity 1 plus pi to the 4th over 4. If s equals 3, then capital A of k and n tends to infinity, as can be seen from the following relation, where capital A of n to the s and n is equal to 2n times sine of pi over n times the square root of the quantity 1 plus 4 times n to the 2s times sine to the 4th of pi over 2n closed quantity. We have thus obtained the following result. When a sequence of polyhedra converges to a portion S of a surface, the area of these polyhedra may not converge to the area of S. Analogous difficulties do not arise in connection with the definition of the arc length, since, according to the mean value theorem of differential calculus, the direction of a chord AB of a curve C tends to the direction of the tangent to C at A if B tends to A. We finally mention without proof the fact that the area of a portion S of a curved surface can be defined by using sequences of polyhedra with vertices on S. In the case of the above example, we have that capital A of k and n is greater than or equal to 2n sine of pi over n. In the case of any surface, the limit of the areas of polyhedra of the type under consideration, if it exists, is always greater than or at least equal to the area of the curved portion S of the surface. If, for every sequence of such polyhedra, we find the lower limit of the areas, these numbers form a set of numbers associated with S. The area of S can be defined as the lower limit, or lower point of accumulation, of this set of numbers. And in the final stretch, we come to the problems. Problem 37.1. 37.1. Compute the area of the portion of the cone given by x of u1, u2, which is equal to u1 cosine u2 in the first entry, then u1 sine u2 in the second entry, and in the third entry, a times u1, which is determined by x3 being greater than or equal to 0 and less than or equal to, I guess, capital B, a constant. So we have that g sub 1, 1 is equal to 1 plus a squared, and then g sub 1, 2 is equal to 0, and then g sub 2, 2 is equal to the square of u1. We then also have that d capital A is equal to the square root of the product of first the quantity 1 plus a squared closed quantity and then u1, and this is du1 du2. The value x3 equals capital B corresponds to u1 equal to capital B over a. We thus find that capital A is equal to capital B squared over a squared, then times pi, then times the square root of the quantity 1 plus a squared closed quantity. Problem 37.2. Determine the element of area of a surface represented in the implicit form where x3 is equal to a function capital F of x1 and x2. So we set x1 equal to u1 and x2 equal to u2. Then this implicit function takes the form x of u1, u2 equals, in the first entry u1, then the second entry u2, and then in the third entry capital F of u1, u2. Thus we have that g sub 1, 1 equals 1 plus the square of partial capital F partial u1, and then g sub 1, 2 is equal to the product of partial capital F partial u1 and partial capital F partial u2, and then we have g sub 2, 2 equals 1 plus the square of partial capital F partial u2. Hence, replacing u1 and u2 by x1 and x2 respectively, we obtain that d capital A equals the square root of the quantity 1 plus the square of partial capital F partial x1 plus partial capital F partial x2 squared closed quantity dx1 dx2. And finally, problem 37.3, determine the element of area of an arbitrary surface of revolution and use the expression obtained to compute the area of the sphere. So we used the representation occurring in the answer to a previous problem in section 28. Then d capital A is equal to u2 times the square root of the quantity 1 plus the square of dh du2 closed quantity, which is then du1 du2. In the case of a sphere of radius r, we have x3 squared plus u2 squared is equal to r squared, hence h equals the square root of the quantity r squared minus the square of u2. Closed quantity. The area of a hemisphere is therefore given by the integral capital A equals the limit where epsilon approaches 0 of the double integral where the outer integral is from epsilon to r minus epsilon and the inner integral is from 0 to 2 pi of a fraction whose numerator is u2 times r and whose denominator is the square root of the quantity r squared minus u2 squared closed quantity. Then these integrals are du1 du2. Then capital A is thus equal to 2 pi r times the limit where epsilon goes to 0 of the integral from epsilon to r minus epsilon of the fraction with the numerator u2 and the denominator of the square root of the quantity r squared minus u2 squared. Then the integral is du2. This all resolves to be equal to 2 pi r squared. And that's it. I'll see you guys in the next one. Peace.